Lab 3, Black Hole Lab. In this lab, we observed the motion of a star and used the observations to identify the forces. Unlike the other labs where we predicted the motion of an object using initial conditions, we are essentially going backwards in this lab. We are using the object's motion to identify the initial conditions, which, in this case, is the mass of the black hole. The models that are relevant to this lab are the gravitational force equation and Newton's second law. Newton's second law is the change in velocity divided by the change in time and multiplied by the mass. This equation can then be rearranged as the change in momentum divided by the change in time. This equation calculates the net force of a system. The other equation that is important to this lab is the gravitational force equation. This equation allows us to calculate the mass of the black hole. Since the star is in orbit around the black hole, the gravitational force is the same as it is on the black hole. Since we have the initial conditions of the star, it is possible for us to calculate the net force on the star, which is the same value as on the black hole. Then, using the gravitational force equation, it is possible to calculate the mass of the black hole. To calculate the net force, we first calculate the change in velocity of the star from the CSV file. These lines of code here are used to find the x and y components of the star's velocity. Then we calculate the final and initial velocity by finding the change in velocity between two time periods, and then dividing that value by the change in time. Next, we found the initial and final momentum by multiplying the star's mass and the star's initial and final velocities. From these values, we were able to calculate the change in velocity and the change in momentum. From Newton's second law, we know that the net force is the change in momentum over the change in time, and this line of code finds the net force. The next few lines of codes are used to calculate the perpendicular and parallel components of the net force. The parallel component is the magnitude of dp dt multiplied by p hat. We find p hat by dividing initial momentum and the magnitude of the initial momentum. Change in the magnitude of the momentum is calculated by subtracting the final and initial momentum and dividing that answer by the change in time. Thus, we have the values we need to calculate the parallel component of the net force. The next component we need to find is the perpendicular component, which is found by subtracting the net force and the parallel component of the net force. The net force can be decomposed into two components, and if we add the perpendicular and the parallel components, we find the overall net force. In order to find the mass of the black hole, I used the gravitational force equation F equals G times m1 times m2 over r squared. We already have the net force, which is the value we calculated from the initial conditions of the star, and we have mass 1, which is the mass of the star. G is the universal gravitational constant, and r is the distance between the star and the black hole. To find r, I subtracted the star's position and the black hole's position. Then, I rearranged the equation so that I isolated mass 2 on the left side of the equation and the rest of the variables on the right side. The calculated mass 2 is the mass of the black hole, which came out to be 1.99 times e to the 34 kilograms. Here's the code when it is run. We can see all of the components of the net force. F net perpendicular always faces the black hole, and F net parallel follows the direction of motion. The net momentum and its components only differ from the net force and its components in the way that they are calculated. Numerically, they are the same values.